Okay, so from here on out, we're talking about electrical properties of materials, and I'm just going to cover as much ground as I can in the lectures we have left.
So superconductors?
Actually, I'm not going to get to them today, because that is, in fact, the place where I randomly selected to leave off with my notes. So yeah, we'll get to superconductors eventually.
Actually, in general, though.
In general, we should be able to get to that, yes. So some of this is stuff you should already know, and then obviously some of it, hopefully, is things you don't know yet. Okay. So electrical conduction, what is the primary material property that we would use to characterize electrical conduction?
Resistance?
Nope.
Conductance.
No. Here it is. The material property.
Thermoconductor.
Density.
Oh, shut up. Duck, duck, duck. Are you playing duck, duck, goose in the back row there? What is it? Huh?
Ductility?
Ductility? No. For electrical. Electrical.
Oh, no! Conductivity.
Conductivity. Duh. Hello.
Wait, who says conductor?
Conductivity. That is the material property. It's a relative ability to move electrical charge. And there are three types of charge carriers. That we're going to be concerned with. First, electrons. Where Q is equal to what?
Something times 10 minus 16.
1.8.
1.619.
What is it?
1.619
Times?
times 10 to the negative 19.
Okay. I don't know about the.
1.602.
Oh, 2, that's it.
Yeah.
That's it.
1 EV.
Okay.
1 EV. No, EV is a unit of energy.
I was in kilocharge.
All right. Is that correct?
4 times 10.
Cool.
No. Well, yes, coulombs, but that's not what I'm looking for. It's negative. Thank you, Ben Franklin. All right. Ben Franklin's the one who decided what was going to be negative. You know that, right?
Didn't do that at one point. I couldn't put you on top of
He's the one who had vitreous charge and resonance charge, and decided which one was going to be positive. He didn't like those names, so he made one positive, one negative, randomly.
Wait, so he was before like Coulomb and Maxwell and like
So,
Ampere and
Considering that that was the 1800s and he was in the 1700s, yes.
no, all of those guys from the 1800s.
not before Newton. No, not before Newton. Although Ben Franklin was kind of an old guy, so maybe you know.
And Ptolemy and
All right. The second one. Anybody want to guess what the second most popular charge carrier is?
Proton.
No.
Strange
not
quark.
protons. No.
Electrons.
Oh, Britain. Electron holes.
What?
What? Exactly.
Black hole?
Q there is going to be 1.602 times 10 to the minus 19 coulombs.
Positive.
So it's like a positron.
it's
It's the absence of.
It is not a proton. It is an electron hole. We'll talk more. And then the third most popular are ions. So a proton would be an ion, right? It's a hydrogen, an ionized hydrogen atom. Q here equals Z times 1.602 times 10 to the minus 19. Oops, 19 coulombs. Where Z is the valence of the ion.
plus or minus Z.
Z would be plus or minus. So the valence for oxygen is -2. Okay. Generally speaking, everything we deal with in here is solids, and ions are relatively immobile in solid materials. So we're really only going to focus on the first two. But in liquids, ions are a significant contributor. C, magnetohydrodynamic propulsion. Oh yeah, you should know that.
Can you say that again?
Magnetohydrodynamic propulsion.
Magneto?
Magnetohydrodynamic propulsion.
Sounds like I need.
That's where you basically, it's a worm, as silent drive on a submarine. use electrical fields and magnetic fields to exert a force on the ions in the water. So
That's cool.
that's our third law of force in the other direction. All right. Okay, so again, we're going to focus primarily on these two. Right, that's what we're mainly concerned about.
Joel was distracted.
Maybe bring one of you to the front row. Okay. Now, macroscopically, the most basic principle of electrical conductivity or electrical conduction equals IR, Ohm's law. Right, voltage, current, and resistance. And we typically represent R as rho L over A. What's rho?
Density.
No, it is not.
Isn't it the conductivity?
It is not the conductivity.
Permissivity.
Resistivity. What did you say? Permissivity?
Permissivity.
Conduct.
No, that's what you have from liberal parents. I'm sorry. So I said so right. Resistivity. And it is actually equal to 1 over sigma, where sigma is the conductivity. Okay. L is the length of the conductor, and A is the cross-sectional area of the conductor. So this is why resistance is not a material property. Right? It depends on the geometry of the material. Resistivity is, on the other hand, a material property. But typically, in terms of the actual what's going on, we define conductivity and then invert it to get resistivity. Okay.
Why do we do conductivity? It's just easier to calculate
See in
conductivity?
just a minute. Always ask in the next question. So conductivity is defined as N, Q, mu, where N is the number of charge carriers available to do the conduction. Q is the charge of each carrier. And mu is the mobility, the electron or electron hole mobility. So it defines how easily that charge can move through the material. So the total conductivity is going to be a combination of the, well, here, let's just do it this way. The conductivity of the positive and negative charges. So I can move, so if you think about it again in the magnetohydrodynamics case, I can move both chlorine ions and sodium ions in salt water. Right? If I move one sodium atom from here to here, I've conducted a positive charge that direction. If I move a chlorine atom from here to here, I've also conducted one positive charge in that direction. Right? Both of those represent a conduction of charge. Okay, so just in general, for metals, sigma is on the order of 10 to the 7th-ish. And then the units here are moles per meter.
Moles per meter.
Moles per meter.
Per meter.
So mo is a 1 over an ohm. So OHM spelled backwards is MHO. I'll leave that, right? So the mo per meter. Then sigma for insulators on the order of 10 to the minus 10 to 10 to the minus 16, again, moles per meter. And for semiconductors, it's on the order of 10 to the minus 4 to 10 to the 4. all ballparks. Get you in the general ballpark. So we have very high conductivity, very low conductivity, and intermediate values of conductivity. Okay. All right. So let's talk a little bit about where these conduction things come from. So we're going to do a little chemistry. What would normally be covered in chemistry. You'll have to tell me if you actually cover this in chemistry. So energy bands.
Pretty much anything that's related to engineering or physics, he goes, oh yeah, you'll take an engineering course if you want to look into that.
Pretty much.
Really?
Pretty much.
Like what?
Like all the crystalline structures, if you want to know more about that, take an engineering course.
He
Seriously?
briefly like said what they were and gave like a diagram of it, like a minute, and then he's like, but you learn this in engineering class, you need acting on it.
Or then I guess it's a chemistry class too.
Yeah, so if you can bring us.
Fine, special.
Interesting. By inspection.
He literally
By
says
semesters.
you don't need to know it right now.
Yeah.
It just shows picture.
Well, then you feel like you've learned something in material science. Yeah, that's good.
Yeah, keep
Okay. So energy bands. One of the key principles that we're going to use in discussing energy bands, the Pauli exclusion principle. Anybody know what that is?
One electron can operate in one energy.
What's that?
Spins of
We actually just
electrons.
talked,
Yeah, we're talking about
Dr. Davis
ENM.
just briefly mentioned it, I don't know if he had quite the right thing, because I seem to remember it being something slightly different.
I think it was spins.
But that's
of-
okay, if somebody can spit it out, it'll be good.
Electrons
They didn't really
spins,
say what it was.
Like,
What?
two electrons can't have the same spin in the same orbital?
So the Pauli exclusion principle is two electrons cannot occupy the same state. It's
Yeah.
not just about spin.
Right.
It also involves energy or momentum, whatever it has to be. They cannot occupy the same state in the same chunk of material, you know, in the same area, orbital. Yeah. So, sodium. We have one S2. In other words, there's two electrons in the 1s orbital. 2s2, 2p6, 3s1. Does everybody recognize that nomenclature from chemistry, hopefully? Right? Okay, so if I were to take one atom and draw it out at 3p, the 3s, the 2p, the 2s, the 1s, and I've got an up and a down, right? And then just an up. Right? Another way of representing. I can also represent them on an energy diagram. And here, the horizontal axis is meaningless. Okay, it has no significance other than to give us dimensions so that we can draw things on the vertical axis. So we have two 1s energies. Right, two electrons, again, you have to have different states, they have a slightly different energy. Then we have a pair of 2s, a bunch of 2p, and then a 3s, and there's only one. And there would actually be another level potentially available for this one. Right? If we want to fill that band. Does that make sense to everybody? Okay. Now, I'm going to come in, I'm going to add a second atom, which has its own 3s, 2p, 2s, 1s, right? So it's got its own, you get the general idea, right? And then an empty layer of its own. Now, if these two atoms are connected together, they're in the same material, they can't occupy the same level. So I have to have my 1s have to be interspersed between my other 1s's. Because they can't have the same energy state. They have to have,
Really?
Why not?
Really?
Oh, really?
And then my 2 S's, slightly different energy. My 3 S's, right, and so on. You're getting the idea.
So,
And then,
does that do the fact that we can only measure things? I mean, like, to us, it might appear that
Ties
they're the
into
same
relativity principle.
energy. But like, to us, they might appear that they're the same energy.
right,
But if you're able to
they are
measure-
microscopically, if that were actually meaningful in this context, different energies.
Okay.
Minutely
So,
different energies.
So like 100 decimal place
Whatever,
potentially or something
right,
like
yeah,
that.
slightly different energies. Did you have a question?
That's kind of, like, the Pauli exclusion principle come out just like from the math.
Does it come out
Does
from
it
just
come
the
out
math?
from math, like we just kind of figured it out through that, or is it some measurable process that we figured out that can only do that? Only.
So, I think it's probably more the latter than the former. It's a fundamental characteristic of the nature of the universe that we uncovered than it is sort of a mathematical construct. Okay.
Sorry, what, are the black and the red lines representing two different things?
The red lines are for the second atom, the black lines are for the first
Oh,
atom.
those are two, okay.
Are they bonded together or?
So, yeah, so we have 2 atoms existing together,
Okay.
right, in a particular chunk of material, right? And then we can add a third atom, right, so we end up with, all my blue markers are toast today.
Oh!
I like the first
Oh, you're
time.
coming off Thanksgiving
Cancel
break.
class.
We're done here.
You haven't been able to practice over the weekend here.
There it is. You grabbed the green one.
All right, got the green one next, we're gonna try the green. It is after all Christmas, okay. Here's green, so I add a third atom, right?
Okay, so when you have a material with billions of sodium atoms, then
Precisely. When you have a material with billions and billions of atoms. Anybody know? Carl Sagan?
PBS, show.
No, not that one. Carl Sagan, who actually never said billions and billions, but everybody says that he does, so.
What?
So what you end up with, when you have
1814 took the trip.
that lost so much.
If I threw a marker, it would have been there.
yeah, but then I might have hit him and.
Then I
could have
said. Caught on camera.
The camera's
So what we really end up with when we have those billions and billions of electrons is something that looks like this. I'm making this much wider than it needs to be, I don't know why. We have what essentially are quasi-continuous bands of energy. No, it's not at all.
I'm gonna throw something at you.
Okay, so we have quasi-continuous bands of energy, meaning even though there are discrete distinctions between the energies of the various electrons, those distinctions are so minute that it effectively becomes a continuous band of energies. So all of the electrons are distributed uniformly around within this energy band. Okay, and then here's the 1s, the 2s, the 2p, and the 3s energy band. Okay? That make sense? Okay. So, okay, so now if you look for sodium here, you'll notice that this top, let's put that back. Oh, thank you. Very nice. You notice this top band is only half full, right? For the sodium. And at 0 Kelvin, at absolute zero, it's the bottom half of the band. Right, makes sense. Lowest possible energies.
0 Kelvin.
What's that?
See, 0 Kelvin?
At 0 Kelvin, the filled half will be the lower half, the lower energy half of the band.
Oh, okay, okay.
Because there's no thermal energy to excite it to a higher energy. Right. So all I would have to do in this case then, for the sodium, is to apply a potential, right, which is an energy per unit charge. Right? That's what voltage is. It's energy joules per coulomb. If I apply a potential, I increase the energy of some of these, and they're free to move. Right? I increase this energy, and it can again, the horizontals does not actually represent physical dimension, but nonetheless, I energize an electron up into the space. It can be there. It can accept that additional energy and change, because if now I make this dimensional, I excite an electron on this side. It's got a higher energy. There's a low energy side over there. It's going to want to move. Right? That's what the voltage does. It creates a force, a potential pushing it across the side, and it's free to do so because it can exist there. Does that make sense? So that's where conductivity comes from. Therefore, because an electron here can be excited up there, sodium is conductive. I can add a little bit of juice, a little bit of voltage, and the electron has somewhere to go at that slightly higher energy, and therefore can conduct across.
So would magnesium then also be conductive or not?
Oh, so let's talk about magnesium. What does magnesium do?
It has like the double.
Now, what's its structure?
It's a 3s2, right?
Right. So magnesium now, this is filled. Right, I'm not going to do it with the red one. Right. So now, magnesium, the whole thing is filled. Right. Magnesium's next on the. So I keep looking over here like there should be a chart over there.
We can draw one up.
Periodic table, thank you. But what happens with magnesium is the 3p level is actually right here.
Because they're all so close together.
So the 3p level overlaps the 3s level in magnesium. So the magnesium is also conductive because they can jump in energy. Ever so slight energy change just pushes that electron into the 3p orbital, and now it's free to move.
So I can't remember which one it is, but the one like right below hydrogen. Would that one be able to do that then? Because if they're not as close,
Lithium?
the one next to that.
Beryllium next.
Is that conductive then? Because the 2s is close to 2p, or is it just less conductive?
I don't know.
That's fine.
Beryllium and iron.
You want to answer your question now?
So would something similar happen with the element before sodium that I can't think of off the top of my head, where the 2p orbital is filled, would the 3s orbital kind of overlap it a little bit, and it would be conductive, or
So
what comes?
sodium is the far left end of the spectrum. The one
Oh,
right
so it'd be
before
a
it
noble gas.
would be a noble gas,
Okay.
yeah, so it's not
Okay.
going to, unless you ionize it.
Yeah. Would that happen then in between the 2s and the 2p? So if the 2s was filled, would the 2p overlap it?
So
Or
I'm
is
trying
it
to figure out
just
what,
between-
I'm trying to think what would be, so lithium is where the 2s is open, so beryllium is the 2s and 2p, which is
Okay.
what we were talking about, and I have no idea
Okay.
what beryllium structure is. But anyway, so that's why magnesium is conductive, because it has some place to go. Okay, does that kind of make sense to everybody, the general idea? Conductivity, I need to have some place for that top electron to go. Okay. We call these, by the way, in this case for magnesium, this would be the conduction band, the 3p. And the 3s would be the valence band. So the valence band is the band of in which the highest order or the highest energy electron exists at 0 degrees Kelvin. The conduction band is the band in which electrons must move, so it is the lowest unoccupied electron energy. Yes.
So what about the previous one where we were doing sodium? Are the conduction band and the valence band the same?
Right, they're both 3s. The 3s is both the conduction and the valence band. Okay? All right. Now we'll talk a little bit about the electron distribution. So instead of just talking about it sort of statically, right, that's kind of just a static picture of where the electrons are, we're going to talk about it a little bit more dynamically. So at T equals 0 Kelvin, now I'm going to plot energy on the horizontal scale. It's the same energy, I'm just plotting it on the horizontal scale, because I'm going to plot a probability distribution, F of E. It's the probability of finding an electron at a particular energy. So at 0 Kelvin, it's something like this. So for the sodium, this, I'm going to use a lowercase energy, lowercase f? Yeah, I did. So, I'm sorry, F of E is the probability of finding an electron at E. So at 0 Kelvin, it's 1 everywhere below E sub F, and 0 everywhere above it. E sub F is there, it is called the Fermi energy. And F of E is the Fermi function. Yes?
So if this is the same energy as we had on the vertical axis over there, why isn't it bands like that?
The bands are here, but I'm not showing the bands. So in this case, there would be a band here. Or if I were showing the band, that would be the 3s band of sodium.
Okay, so.
Okay, but the probability function is still a function. It's not discretized, if you will. You'll see as we get going. You'll see as we get going. Okay. So that's at 0 Kelvin. At temperatures greater than 0 Kelvin, the Fermi function does that. Okay. So at temperatures greater than 0 Kelvin, there is a finite probability, right, that there will be an electron, that there will be an electron out here. But there's no band for it to exist in. So it doesn't physically exist there. It's just there's a finite probability that it will have that energy. There's also a finite probability that the electrons will exist here, but they don't actually exist there. There's no band there. You see what I'm saying? This is just determining what is the probability, as you'll see in a second, it's thermally driven, that electrons will occupy any particular energy. And then we have to overlay that with the actual band structure of the material to see where they really exist. Okay, we'll keep digging with it.
Is that actually going to 0 or is that asymptotically going to 0?
Yeah, it's asymptotic. So this Fermi function is 1 over e to the e minus ef over kt plus 1. So it has this Arrhenius behavior embedded in it. Right? You remember the Arrhenius behavior? Some energy barrier divided by kt or rt, depending on whether you're doing it by individual atom or doing it by moles, in moles. So for sodium, EF, the Fermi energy, is in the middle of the 3s band. Because that is the energy at which, at any temperature above 0, immediately above zero, you have a 50% chance of finding, 50-50 chance of finding an electron at that energy. Okay? And it's the highest energy at 0 Kelvin. In magnesium, EF then is the top of the of the 3s band. Right, so for magnesium here, the highest occupied state, the top of the 3s band, that's where the Fermi energy is. So there are three kinds of materials from the standpoint of Fermi energy.
Why wouldn't magnesium be the top of 3P?
Because there's no electron there. It's EF is at 0 Kelvin.
At 0 Kelvin.
At 0 Kelvin, that's where the highest energy electron is, right? And at higher temperatures, that is the energy at which you have a 50% probability of finding an electron. There's a reducing percent, a decreasing percentage probability of finding one at a higher. And then it increases down to the point where, down here it's 1. Right? We're not going to, at sort of room temperature, we're not exciting electrons from down here in any appreciable numbers. So the probability is down to 1. Again, it's an asymptotic approach. So there is, at room temperature, some finite probability that a 2p electron might be excited into a higher energy state. All right? You have some energized electrons at all times in every material. Right? They're not all just in their pure valence state. But the numbers are very small unless you get to go to high temperatures. If you go to high temperatures, you can get lots of electrons up into many high energy states.
So theoretically, you
Or you can energize them other ways. The arc lamps that you guys used in modern, remember the neon and helium and whatever else you looked at, hydrogen lamps on mercury. Those are, you've energized the electrons, in that case, by bombarding them with mobile electrons. Right? I mean, that's what that, you had to send that plasma, or you send an arc down the center of the gas. You actually energize the electrons into higher orbitals. And then they decay back and emit wavelengths, and you can find out what the orbital structure is. Right? You guys remember that from Mach. So there are other ways of exciting them, but thermally, you have to, in order to excite them, you're using this Fermi function to excite them thermally. It's all driven by T. Okay? That make sense? Okay. So that leaves us with there are three distinct kinds of materials. Which I just actually erased from the board right here. The first is conductors. We talked about conductors, and they had a high conductivity, 10 to the 7th-ish. From an electron, or from an energy standpoint, a conductor is either this, or this. Either way, a conductor is defined by the fact that the Fermi energy is within a band, within an energy band. So for conductors, E sub F is within a band. Not at the edge of a band, but within a band.
So EF is any part of that?
EF is this point, the energy at which you go from 100% probability to 0% probability at T equals 0 Kelvin, or at which the probability is 50% at some temperature above 0 Kelvin.
So, in the second option, EF is
So
the
EF is right
top
here. So in this case, EF would be right here, and it's in the middle of the 3p band. In this case, EF is right here, and it's in the middle of the 3s band. So anytime EF is within a band, it's a conductor. Okay. If the 3p were higher, this would not be within a band, because EF, as it turns out, would actually be halfway between the two. So let's look at the second category. What did I do second? Semiconductors. I did these in different order than I did before. Yeah, just realized I changed my drawing geometry. I'm going to go back to this geometry for the semiconductors. Sorry. All right, so here's my Fermi energy at 0, and then a temperature above 0. Right. So for a semiconductor, the bands are here. So this would be valence band here and the conduction band here. So this would be all full, that would be all empty, and the Fermi energy is halfway between the valence band and the conduction band. That make sense? If I did it horizontally, I'll do it horizontally. So we have the valence band, which is full, and the conduction band, which is empty, and then E sub F, the Fermi energy is halfway between.
So, that, going back to kind of the probability diagrams, and so the function, I understand it can be 1 and then go to 0, but the actual, like, an electron itself is not going to exist outside of
Of the band structure.
Okay.
So if you look at this picture here, the semiconductor, right, at the red temperature, the temperature I've shown here, there are a few electrons from here that have been excited up into the conduction band, but only a few. That's why it's a semiconductor. There's only a limited number of conductors available, charge carriers available to conduct electricity.
I'm trying to figure out how this would work if it got to, actually to 0 Kelvin. Because would there just be some of the electrons would not be within a band?
No, the electrons are all within a band. So if this got to 0 Kelvin, right, you have a 100% probability of finding an electron below that, which means that this band would be full. And the 0% probability of finding them above, so there'd be none in this upper band.
So there's a section of 100% probability that's not in a band then?
Correct. Because you have to, as Joel talked about, you have to superimpose the two together to find out where the electrons actually are.
So then those spots, there's a 100% probability there's never actually going to be one there.
Right,
Because,
it's just like how the lower energy is there, there's gaps in between, where there's 100% probability,
but there's nothing there. Right, so, right, there's 100% probability of having an electron up to that energy. But there's gaps here, there aren't actually electrons in those gaps.
Okay.
You have to take into account both pieces. The Fermi function just tells you about the thermally excited condition of the charge carriers. You have to also overlap that with the band structure to know whether there's actually charge carriers present in that location. And then what we have here for the semiconductor then is this dimension, the width of this space between the conduction and valence band, is the gap band, the gap energy gap, EG. It's the width of the gap between the valence and conduction bands. So you've heard band gap, right? You've heard that term used in electronics, somewhere band gap, maybe not.
Band pass.
What's that?
Band pass.
Band
Band
No.
aid.
Rubber band.
Never mind.
Marching band. AC/DC.
Okay, so then third
Sort of related.
is insulators.
Read the other PCs.
And all an insulator is semiconductor with a really wide band. So that even at moderate temperatures, there are essentially no conductors excited into the conductor. There's a big gap, energy band gap. And again, the Fermi energy is in the center of the gap.
So as you get lower on the periodic table, things will get, there are less insulators then. Is that correct? Because the
Yes, I'm not trying to draw a broad inference. I'm just trying to explain the structure right now.
Okay.
So conductor, okay, so everybody cool with band structures. Okay. So, so conductors up in here defined by this conductivity, right? N, Q, U. So N, we've kind of accounted for here with the Fermi function. How many we have available to conduct. Q is defined by the essence of the conductor, charge carrier. Mu, on the other hand, is the thing that really affects conductivity that we can change. Right? We can change the conductivity of things, of materials, by altering their properties, their characteristics. We can't change N because that's the band structure, the energy band structure we're given. And we can't change Q because that's the charge. So there's three things that can affect, three ways to manipulate sigma by virtue of manipulating mu. Temperature, composition, and strain. Since this is material science, we got to work in something from the earlier chapters. Plastic deformation. In all three of these cases, we're essentially getting something in the way of the electrons. Something gets in the way of the electrons as they're trying to pass through the metal. So with temperature, we can plot, in this case we're going to plot resistivity as a function of temperature. And we get something that looks like this. So copper is going to be the lowest one, aluminum, iron's up here. Because copper is a better conductor than aluminum, has low resistivity. If you plotted conductivity, you would be, they'd be curves like this. That's why we plot resistivity, because it's linear. And you find that resistivity as a function of temperature is equal to whatever the room temperature and whatever baseline resistivity you have times 1 plus alpha delta T. So at least as long as the temperature range, the change in the temperature is fairly small, we can consider that it's a linear behavior, and that in fact the temperature change there's a linear response to temperature change. If you get really large temperature changes, you're probably going to have other things going on in the thermal characteristics of the material, and you're going to be tempering your material, you're going to be changing it from alpha to gamma, whatever. You're likely to be doing other things to the material besides just altering its conductivity or resistivity. Okay. But you should have seen this before, right? You've seen that before in UFIS. Right? That's a UFIS kind of thing. Who's had UFIS most recently? Right? You don't remember? See that UFIS?
I don't remember UFIS.
Nobody remember. Okay. Never mind. Oh, Dr. Davis would be so proud. Okay.
We don't have any classes.
Composition. So if I take, what do I plot this for copper? If I take for copper, I plot the weight percent of an alloy. So I can put some aluminum in the copper. And these numbers are kind of on a, this is 0. This is on a kind of a, 0.2 weight percent, a very small weight percent. So I put a little aluminum in there, or a little iron would be up here. And so you get a little bit of contamination, and those contaminants block the electrons from going through. The electrons are coming in, and all of a sudden I got an iron atom here where I'm expecting to see a bunch of copper atoms, and then iron atom's going to distort the behavior of the electron.
So is that also plotting rho?
What's that?
Is that plotting rho?
Yes, again, probably rho, yes. So again, here, rho is going to be, again, some rho naught times 1 plus, and then we use beta times the weight percent. But it's still a linear behavior. Now, obviously, it can't be a linear behavior indefinitely, right? It's only going to be a linear behavior for some small weight percent. Because if I zoomed out and did this on the phase diagram scale, right? So I go from, my weight percent goes from 0 to 1. This is 0.0, actually I should, this is weight percent, so it's 0 to 0 to 2. Anyway, so in other words, it's very small weight percent. So from 0 to 1, I'm going to start out over here, the resistivity of copper. And over here, I'm going to have the resistivity of aluminum. Right, so it can't possibly be linear all the way across. Otherwise, putting an alloy of copper atoms in aluminum would actually decrease resistivity, which is silly. Right? So they both increase resistivity as you dope them, but eventually they have to round over. Yes.
So pure something is best for.
Pure something is best. That's why, yeah. So a lot of you really want to do some high-end electrical stuff. You're using 5 nines copper, or 6 nines copper. What do you mean by 6 nines? 99.9999% copper. Okay. So how many nines do you have? 99.9999. Anyway, so the point is, there's another linear relationship here, and then if you look at strain cold work, it's a similar behavior. As I strain it, the resistivity goes up. So here's my. So this is percent cold work, and this is the resistivity, and again it does has some kind of behavior like this. Okay. There I don't really have a good strong relationship, but you get the idea. Because here, again, dislocations, lattice strain, all these things are going to inhibit an electron's ability to move uniformly through the lattice. Yes?
Quick question back to rho versus T.
Yeah. That's actually rho versus Wade, but go ahead.
Are we just neglecting, what happens when you get to really low temperatures? Does it stay that linear function?
When it gets to really, really low temperatures, no, actually what will happen eventually is they'll do this.
With that noise, right?
Yeah, with that noise. But those temperatures at which it becomes a superconductor are very low. And doesn't always happen, right? Not everything goes down to, not everything can become a superconductor at low temperatures. But when they do, I assume that's what you were asking about, that's the behavior of the sea. And we'll talk about that when we get to superconductors. All right, I got myself all out of order here. Okay, so I think we've covered up to that. Next time we'll start talking about thermocouples. Pick up the thermocouples and then semiconductors, and then go from there. Does anybody have any questions? I assume, since we're not shy about asking our questions, you don't. But does anybody have any questions?
For the test, and so people have to take it.
Test. Material science test?
Yeah.
Oh, I completely forgot to give it back to you. Try that again on Wednesday. Sorry.
Oh,
Just space.
oh!
Thermal study tonight? Thermal study table?
Thermocoupling?
So, thermal study table?